What's going on, guys? Welcome to LetThereBeMath again. And following from the previous video when we derived a general formula for the integral of any function x to the power of n, we found out that all we need to do to basically find the integral of that function is to add 1 to the power, and then we're going to divide that function by the new power, which is n plus 1. We also discussed how we need to add an arbitrary constant of integration c, because when we take the derivative of a function, we can actually take any function and shift it along the y-axis, and the derivative is still going to look the same. So this arbitrary constant c makes sure that we actually account for any function regardless of its position along the y-axis. Now we're going to take this formula and we're going to apply it to a few simple examples. Now the first one we're going to start with is going to be 2 times x to the power of 3. Now, the constant at the front 2 is not really going to have any impact on our integration procedure because we know it's just going to stay there and it's just multiplying x cubed. So our main focus here is the x cubed function. So what we're going to start off with is we're going to add 1 to the power, so that's going to be x to the power of 4. And we're going to divide that function by the new power, which is 4. And then we're going to add the constant c. Now, of course, if we want to simplify this even further, we can do the simple thing and we're just going to divide both top and bottom by 2. So that's going to become 1 over 2. So that's just half times x to the power of 4. And that's going to be the integral of that function. Following the same procedure again, we can move on to the next section and we see that we have 3 times x to the power of 5. So we're going to leave the constant intact. We're just going to leave it there as 3. And we're going to start off by adding 1 to the power. So that's going to become x to the power of 6. And then we're going to divide it by the new power, which is 6. And we're going to add the arbitrary constant c. So now the next thing is we're going to simplify that fraction. And that's going to become half. So the final answer should be x to the power of 6 divided by 2. Now, what do you think would happen if we now take something that is the inverse of some function? So let's say 1 divided by x to the power of 2. Does this formula still apply to that scenario? And the answer to that is yes, it still applies because we know we can express this in the equivalent form, x to the power of minus 2. And then we have all the x here. And now all we need to do is we're going to add 1 to the power, which is going to make it into x to the power of minus 1. And now we're going to divide that by the power of minus 1. And then we're going to add the constant c. And now to simplify things even further, we could just rewrite this whole expression in the following form. So let's just take the x down. And we're now going to write this down as minus 1 divided by x. And if we wanted to verify that this is indeed the correct answer, all we would need to do is differentiate this, and we would notice that we get back to 1 over x squared. So our formula actually holds for negative powers as well. Now, a very common question you might encounter if you're going through textbooks and exercises is that you will not necessarily have an integer power, you can also have rational powers. So what will we do in the case where we have something like the square root of 2 times x? Well, we know that a square root, or any root for that matter, can be expressed as a fractional power. So we're going to rewrite this in the following way. First of all, let's leave the square root of 2 as it is, because we know that's an irrational number. So we need to leave it as is to keep the exact form. And then we're going to express the x in terms of x to the power of half. Okay, and then let's not forget our element of integration, the x. So now all we need to do is we're going to add 1 to this power. Now we start off with a square root of 2 that remains intact. When we add 1 to a half, we get x to the power of 3 on 2. And now this is going to be divided by the new power, which is 3 on 2. And then we're going to have the constant plus c. Now, of course, we can simplify this even further if we bring that 2 in the denominator all the way up. So now we can express this as 2 times the square root of 2, x to the power of 3 on 2, divided by 3, plus the constant c. And that's essentially going to be our final answer. Now, now that we know how to integrate all these different types of functions, we can ask the question, what happens when you have some kind of compound polynomial like this one? So you have a bunch of terms added together. How does the integration actually happen in this case? Well, here we're going to exploit a property of integrals, and it is that the integral operator is linear. What that means is that if we started off with an expression like this, we have a times some function of x plus b times g, which is another function of x, dx. The integral of that function is going to be the same as the separate integrals of those two functions added together. So that's what linearity means in the context of functions. It means that if you apply that operator to a whole compound function that consists of an addition of different terms, it is going to be the same as applying the integral operator to each of those terms individually and then adding the results together. So we're going to apply this result to this particular example. So now let's just make some room over here so we can actually go through that. Now we're going to apply the integral to each of these functions individually. So just to simplify things a little bit, let me just rewrite this as three separate terms. So we're going to start off with the integral of x squared dx. Then we're going to have the integral 3x dx. And lastly, we're going to have minus the integral of the square root of x cubed dx. Okay, so now we're just going to evaluate each of those integrals individually. Now the first one, we already know what's going to be. We just add 1 to the power, that's x cubed over 3. And that's going to be plus some constant. Let's call it c1, since we anticipate we're going to have constants coming from each of those integrals. For the next integral, we're going to take x to the power of 1 is going to become x squared divided by 2. And that's going to have its own integration constant, which we're going to call c2. And lastly, we're going to integrate the function over here. Now to do this one, we can also represent this as a rational power. So let's take that square root and instead we're going to write it as x to the power of 3 on 2. That way, all we need to do is add 1 to the power. So that's going to give us x to the power of 5 on 2 divided by 5 on 2. And now we're going to add an extra constant c3. Okay, so how does this play out? Well, the first thing we can do is we notice we have 3 integration constants, but it doesn't really matter because they're arbitrary. We don't actually know what they are. We are going to define them depending on which function we're looking at. So what we can do is we can grab all 3 constants and we're going to group it into a single one, which we're going to call c for generality. So now we're just going to express this whole integral as x cubed over 3 plus 3x squared over 2. Minus, now let's bring that 2 all the way to the top. That's going to become 2x to the power of 5 on 2 divided by 5. And now we're going to write all those 3 constants into one, which we're going to call c. So this entire expression over here is going to be our final answer for that integral. Now I hope this video was useful. In the next video, we're going to continue deriving more general results for integrals, and we're going to see how we can apply the exact same techniques to more complicated examples. As always, if you enjoyed the video, make sure you hit the subscribe button if you would like to see more content from LetThereBeMath. I will see you guys in the next video.